tracers incorporated in that carbonate as it grows. Um, all right, so there are many, many different things you can measure in speleothems, but today I'm just going to focus on a few hydroclimate proxies. And they can be interpreted in different ways, but for today, I've sort of broken them into regional hydroclimate versus local hydroclimate change. And this isn't always the case everywhere, but in Southeast Asia and central Vietnam, tends to be how they break down. So oxygen isotopes, which are the most widely measured speleothem proxy, tend to reflect the isotope signature of rainfall. And in the case of Southeast Asia, this is not as much a local rainfall effect, but more of a bigger regional signal. So things like changes in moisture source or upstream rainout. But today I'm mostly going to focus on local hydroclimate proxies, so things like carbon isotopes, magnesium-calcium ratios, and calcium isotopes, which reflect a variety of things, but the primary signature is local hydroclimate, so how much rain is falling at your site. And with these stalagmite records, the Speleothem community has developed these really robust records of hydroclimate. Here's a really famous one that I'm guessing many of you have already seen before, from a Speleothem record from China, over 600,000 years of Asian monsoon history. So that's the green curve here in the middle, where we see oxygen isotopes tracking really nicely with insolation change. And in general, there are a lot of really amazing speleothem records from monsoon regions, just broadly. But as Sayak mentioned in his intro, I'm more interested in hydroclimate change in sort of the Southeast Asia and Indo-Pacific region. As I mentioned, today I'm going to be talking about a stalagmite record from central Vietnam. And one really interesting thing about central Vietnam, which our cave site is the yellow square there, is that unlike most of Southeast Asia, which receives rainfall primarily in the summer monsoon, which is the map on the left, central Vietnam receives the majority of its rainfall during the autumn. So you have the ICCP moving from north to south at the end of summer, causing this seasonal reversal in the winds, and the central Vietnam coast here gets quite a bit of rainfall during September, October, and November. So we're in a really well situated, our study site here, to capture this autumn monsoon signal that currently we still don't know much about. So we don't fully understand autumn monsoon variability, and especially on paleoclimate timescales, there's not a lot of information about this monsoon system. So why do we care about the autumn monsoon? It has really large impacts on the local communities. It's a very seasonal phenomenon, which can cause pretty dramatic flooding. So just a couple of examples, I've included the photo on the left is a hotel that we regularly stay at when we do field work. You'll notice that it's on stilts, and that's because it's near a riverbank that floods, I think, pretty frequently. So they just have their houses built up higher. Another really cool adaptation that the local communities implement is to have what is called a flood house, which is pictured on the right. And it's a little bit hard to see in this photo, but if you look carefully, you can see that at the bottom of this house, there are barrels. So when the water level rises, the house actually floats. It like rises with the water, and it doesn't float away because of these pillars here. So families will have like their normal house, but then during the flood season, if there is a flood, they go into their flood house. So anyways, this monsoon system is particularly volatile, including tropical cyclones as well, also happen during this autumn monsoon season. And last year, I think the Philippines was very much in the news. I think there was like a week where there were a bunch of like tropical cyclones in a row. Well, a lot of these storms also hit central Vietnam as well. So sort of better understanding the variability of this monsoon system is going to be really important for understanding future changes in flooding or extreme events. So our main research questions in a sort of paleoclimate lens can be broken down into, we're interested in how the autumn monsoon has changed in the past. What are the controls on this autumn monsoon variability? What's driving these changes? And then finally, and this is the piece that I've highlighted more in the title of the talk, is how well are the climate models doing at capturing autumn monsoon variability? Because if they're not doing a good job in the past, that doesn't give us a lot of confidence that they're correctly projecting future autumn monsoon changes. Okay, so that brings me to part one, where I'm going to use climate model output to investigate or to help me interpret a stalagmite record. And a lot of the data I'm showing are in papers that are already published, so feel free to check them out if you want to know more. So I'm very lucky that this stalagmite is from a very beautiful study site in central Vietnam in a park called Phong Nha Ke Bang. This park is very famous for having the largest cave in the world, Son Dong Cave. I haven't been there. I think you have to go on a long waiting list and maybe also have a lot of money to visit. But the cave site's actually very close to Son Dong, which is kind of a cool thought. I must mention that our work would not be possible without our collaborations with Vietnamese scientists and also the national park staff. So here are just a couple photos of the team. So the study site itself, photo on the left is us at the entrance of the cave, and then photo on the right is an example of what a lot of the stalagmites look like. So Speleothem folks probably understand right away why this would be a good cave for study. It has a ton of these really long candlestick-shaped stalagmites everywhere. And the first time we visited, we noticed all of these broken pieces of stalagmite on the ground, and we spent maybe half an hour trying to fit them all together. And what we eventually found was this enormous 4-meter long stalagmite that had toppled over and broken into a bunch of pieces. And you'll probably also notice that this isn't a traditional sample photo. I am in my pajamas in my apartment. You might wonder why that's the case. Well, the reason is the timing of when we collected this sample. So really fortunate that we were able to go in the field in early March, sort of right before the world all shut down. And by the time I got back with this sample, the university was closed, everything was in lockdown. So naturally, I brought the stalagmite home with me, and a lot of the data I'm presenting today, some of the very early drilling that was done on the sample was actually done in my apartment. And then finally, this is an international audience, so I'm not sure how well this will land, but this is a photo of me in my apartment polishing the stalagmite while watching Tiger King, which is maybe the most pandemic thing that happened to me the whole time. Weird to think about now. So back to the science. So stalagmite HH1, HH standing for Hua Hung Cave, was dated to have grown from about 45,000 years ago to 4,000 years ago. So it's covering a good chunk of the LGM, the deglaciation, and the Holocene. So we're covering a good time period to see how the autumn monsoon has changed over these big, large climate forcings. So what did the data actually show? So here I am showing a stacked plot of the HH1 record, so a bunch of different proxies. So on the bottom is carbon isotopes. This purple record is the magnesium-calcium ratios, uranium isotopes, and growth rate on top. And just for the sake of time, the uranium isotopes generally reflect weathering, magnesium, calcium, and the carbon isotopes are mainly driven by a process called prior calcite precipitation, which I'll talk a little bit more about later. But just for now, these proxies generally reflect changes in local hydrology. So we expect them to all sort of show the same thing. And some quick observations that you've probably already made is that the proxies all look very similar, which is encouraging. It means that they're likely reflecting the same climate drivers. The other thing is that this record, you can see some really big changes in the record. For example, during the LGM, it appears to be pretty dry. whereas during the Holocene, it was much wetter. And there are many periods in the record where there are these really abrupt, like wet to dry shifts. So there's a lot of variability in this autumn monsoon record, which is interesting. So what does it mean? Like, how do we interpret it? Um, the next step was I wanted to see if the autumn monsoon looked like any other regional records because perhaps they're experiencing the same, it's experiencing or responding to the same forcings. So that's what I'm showing here. Again, this is the carbon isotopes from HH1. So I compared it to the winter and the summer monsoon records and didn't really see similarities with either. And then compared it to dozens and dozens and dozens of other things and also didn't notice any similarities. Starting to panic, but then I eventually started to notice some similarities between my record, so HH1 here, and sea level on the bottom. And just to train your eye a little bit for what I'm talking about, I saw wetter conditions when sea level was higher. As sea level decreases, we see drying in the HH1 record, dry conditions during the LGM, and then an abrupt transition to wet conditions when sea level starts to rise. So I made this observation, but I didn't really understand why, sea level and the autumn monsoon might be linked, and I didn't really have any evidence to back it up. So this is when I turned to climate models. Like, can climate models help me figure out what's going on with this record? And the climate model I'm going to talk about today that I used is called iTrace, which is a transient climate model simulation that was run from 20,000 years to 11,000 years ago. So it covers that interesting deglaciation period. Another really cool thing about iTrace is that it has different runs, so you can look at different forcings in the model individually. So you can really tease out sort of the model response to different forcings. So sea level, greenhouse gases, et cetera. So it's a really powerful tool. Okay, so what I'm showing here now is I'm comparing the iTrace time series of precipitation from the grid cell encompassing the study site and comparing that with the proxy data that are plotted up here. So if we look at the iTrace time series, I have annual precipitation plotted as purple, summer precipitation as green, and autumn precipitation as brown. And what stood out to me right away was this same dry to wet shift at around 14,000 years ago. I was so excited when I first plotted this that it appears that the climate model and the proxies are showing the same thing, at least for this time period. There's some notable differences, like iTrace shows drying during the Younger Dryas, and we don't see much of a signal in our record. And then this event at around 16,000 years ago, iTrace doesn't resolve that either. So it's not perfect, but this really big dry to wet shift, it seems to be capturing, which is really exciting. And the other thing to note is that this shift is not driven by the summer precipitation, like the green curve. It's more driven by this change in autumn rainfall. So this is more evidence that we think we have an autumn monsoon record here. Now, when we look at this in mapped space, we can see that, again, that we're really getting this drying signature in the autumn versus a more muted signature in the summer. And this is, I should say, rainfall anomalies across either side of this sort of dry-wet shift. If we look at the same pattern, so more climate model output, we just zoom out a little bit and we look at the sea level specific forcing. Again, we see that there's this really strong drying signal right over the North-South China Sea and encompassing our study site. So that's really exciting. It seems that the climate models are sort of backing up that initial observation that I made, and that sea level changes are causing this drying that we're seeing during the LGM. This was when I finally plotted for the first time how shorelines had changed, particularly during the LGM. And what I was surprised to find was that conditions at my study site, right, today, Hua Hung Cave is pretty coastal, but back during the last glacial maximum, it was actually pretty far inland. And you can imagine if you're moving if a site is at once coastal, now is super inland, that you could get a change in precipitation regime. So to understand better sort of the dynamics of what's going on, I went back to iTrace and delved more into what exactly was happening during this sort of dry to wet shift. And we found that there was anomalous subsidence over this exposed land in the Gulf of Tonkin and this South China Shelf. This land is cooler than it would be if it was water. So essentially, we have cooler, drier air that is delivering less moisture to central Vietnam when sea level is low. So that's sort of the dynamics we think are going on. And I'll remind you that the monsoon rainfall track is sort of right over this region where there would be the exposed land. So just to sum it up, if we go back to our record again, if we zoom in on this period where we have a rapid dry to wet shift, so this is the carbon isotopes here, we see that it corresponds with this really abrupt change in sea level. And when we look at that in terms of how the shoreline has changed, we see that in a really short period of time, in a matter of several hundred years, we're getting a big opening of, or I guess, filling in of water in the Gulf of Tonkin and a receding coastline of the South China Shelf. So we think it's these small changes which are causing these really big responses in autumn monsoon rainfall. So to summarize part one and to go back to my research questions, we found that there were really abrupt, like dried to wet conditions and big changes in rainfall in the past. We found that sea level was the primary driver of these big shifts, with dry conditions happening during sea level low stands. And then finally, iTrace did a pretty good job. It showed very similar timing to what our record was showing, which was exciting. And I can confidently say that without iTrace, I don't know if I ever would have felt particularly confident with my sea level connection. So I'd say that the climate model was pretty instrumental into how I ended up interpreting the data. Okay, so that brings us to part two. I've established this new stalagmite record from central Vietnam, and now we're going to use it to try to comment on how well climate models are simulating past rainfall in central Vietnam. So the motivation for this part is that most paleoclimate records of hydroclimate are qualitative, and this includes speleothems. And what I mean by that is most proxies describe things as wetter or drier, which is very powerful and very valuable, but can limit comparisons to climate models a bit. You know, you can comment whether the climate models are getting the sign of the, hydroclimate change right, but it's a little bit harder to comment on whether the climate models are getting the magnitude of precipitation change correct. And if we can't sort of narrow that down, it's going to limit how confident we are with the climate models in future projections. So in Speleothem world, I think the community has been trying to tackle this problem for a while now, and I'm going to talk about a couple of proxies that we can use to generate what's called now semi-quantitative rainfall reconstructions. The first are calcium isotopes, which I think are a slightly newer proxy. They've been around for a bit, but not really widely measured. And then the second are magnesium calcium ratios, which are very commonly measured in Speleothem world. So sort of two different approaches to get at this semi-quantitative approach. And just as a reminder, magnesium, calcium, and calcium isotopes both strongly reflect local hydroclimate change. There are other controls on both of these proxies which can complicate the interpretation of what I'm doing next, but for simplicity today, mostly interpreting them as proxies for local hydroclimate change. And the main driver of that being this process called prior calcite precipitation. So I'm guessing most people on the call already know what this is, but I I will explain it briefly now, or at least try to. So prior calcite precipitation is any calcite that precipitates out of the drip water as it's moving through the karst, either in the epikarst above the cave or on the cave ceiling before the drip water is precipitated into a stalagmite. So what goes on is you have water infiltrating through some karst, you have some sort of precipitation event. Maybe you've reached like a pocket in the karst, some CO2 degases from your water. You leave a little bit of calcite behind. And every time you do that, you change the geochemistry of your drip water. In this case, it causes calcium isotopes to increase and magnesium calcium ratios to increase. And PCP tends to increase as conditions are drier. So essentially, um, what's recorded in the stalagmite is a history of how much PCP has occurred, which is then related to how much rainfall is above your cave. So PCP is kind of the heart of both methods for calcium isotopes and magnesium calcium ratios. So to spell that out, you have your magnesium calcium or calcium isotope value from your speleothem. You back out the PCP amount or this F value here, and then you have a established relationship between PCP amount and rainfall to eventually get your rainfall reconstruction. And I'll say that I'm going to briefly go through the methods. I don't have a ton of time left, it looks like. So I'll really briefly go through the methods, but I think the takeaway here is that right now these methods are called semi-quantitative because there are quite a few assumptions that are made. So just take the results a little bit with a grain of salt. They're not like definitive absolute rainfall amounts. So step one for calcium isotopes, you calculate a site-specific fractionation factor. So you need to measure calcium isotope of like drip water, modern calcite, bedrock, and then using a Rayleigh fractionation relationship, you back out how much PCP has occurred in the drip water, essentially. With magnesium calcium ratios, it's a little bit simpler. You assume your minimum magnesium calcium value is sort of your 0 PCP mark. And then you do a simple ratio with, your magnesium calcium measurement from your Speleothem. So I know that was really quick. These methods aren't new, so I'd encourage you to check out the papers I have cited if you want to know more. And then step two, this is where one of the big assumptions is made, is that you assume there's a linear relationship between precipitation amount and PCP amount. So for example, if rainfall has decreased by 50%, you would expect a 50% change in PCP amount. So those are sort of the two main steps to back out rainfall amount. Okay, so that was a lot of setup. So I'm going to measure, I already have my magnesium calcium ratios, and now I need to add the calcium isotopes and then convert them both into precipitation amount. So what I'm showing here is another stacked plot. I have the HH1 calcium isotopes plotted in blue, and here's the magnesium calcium magnesium calcium ratios plotted in yellow down here. The main takeaway is that the calcium isotopes look like sea level. They look like the magnesium calcium ratios. So this is giving us confidence that the calcium isotopes are in fact recording PCP or reflecting PCP, and that they're showing the same climate story that I just presented in part one, which is a good sign. It means that likely it's reflecting precipitation change. Step two is then to convert these two proxies into rainfall time series. So to zoom in on that a little bit, just so we can see it a little bit better. So I have the magnesium calcium precipitation reconstruction in orange and the calcium isotopes in purple. And from first glance, you can see they look very similar, which makes sense because the original time series looked similar. There's a lot of really interesting things going on in this graph that I don't have a ton of time to talk about. So today I'm just going to focus on the fact that In both time series, the LGM was about 50% drier than modern times. So this light dashed line here, we can see that it was very dry during the LGM compared to the Holocene, where maybe it was about modern levels, says the magnesium, calcium, and a little bit drier if you believe the calcium isotopes. So that's what I'm going to focus on for today, this really dry LGM. So we want to see, do the climate models show a similar value? Is this 50% drier like a reasonable value that the climate models are also detecting? So if we go back, or I got ahead of myself. So one important thing to know about climate models are, especially in this region or at this study site, are some of the biases that they have, and that will affect how we interpret the climate model output. So what I'm showing here is a seasonal cycle of rainfall. The observations are in the black, so we see this really big peak during the autumn where we expect to get the most rainfall. But the climate models have a hard time resolving this, mostly due to coarse topography. And what ends up happening is they tend to way overestimate summer rainfall and underestimate autumn rainfall. So that's important to keep in mind when we look at the climate model results I'm about to show. Okay, so now I'm going back to iTrace, that transient climate model simulation, and I'm plotting rainfall amount from iTrace against rainfall amount from the HH1 record. And we can see right away that if we look at annual rainfall, which is this red curve here, it only shows about like a maybe 10 to 20% decrease during the LGM, which is way less dry than what our proxy records show. But when we look at the autumn rainfall, if just autumn rainfall, we see that it agrees with what the proxy records are showing. It's showing a decrease in autumn rainfall of about 50%, which is pretty exciting. And the reason why I think the annual rainfall is so wet is because of that summer bias. So if we just looked at the annual rainfall, we wouldn't think iTrace was doing a very good job. But if you factor in just the autumn rainfall, it looks pretty good, pretty spot on, which is exciting. So that's just one climate model. I also looked at the PMIP4, CMIP6 climate models. So what I'm showing here is just the precipitation anomaly during the LGM. And again, I have my HH1 values here, which range from about maybe 45% drying to 65%. If we look at the anomalies of annual rainfall from these climate models, they are pretty wet still. They show, moderate drying, maybe around an average of around 10% drying. But if we isolate just the autumn rainfall in these models, they show a bigger spread, but some of the models are plotting much closer to our values that we get from our proxies. So I think this is very encouraging. There are uncertainties in the proxies, and obviously there are uncertainties in the models as well, but they are sort of converging if we look at autumn rainfall on this pretty strong dry signature during the LGM, which is exciting. And we'd miss this if we only looked at the annual rainfall. Okay. So to sum up, what did we gain from these calcium isotope and magnesium calcium reconstructions? We think that the LGM, or at least the reconstructions, are showing that it was up to 50% drier than present day, which is pretty crazy. And how did the climate models do? It seems like both iTrace and a lot of the PMIP4 models, they are seasonally biased if you look at the annual rainfall. But we see some decent proxy model agreement when we're just looking at autumn rainfall change. So let's see. I'll wrap up with that, and I will take any questions.
Thank you, Elizabeth, for this nice presentation. The floor is now open for question and answer session. If you have any questions, just please. Yeah.
Very nice talk, Elizabeth. Thanks. I think it's very interesting. So for the in your record, you see a very large jump at 26 to 29,000 years.
Yes.
Do you have any idea what is causing that? Because you don't see anything happening in sea level.
Now, let me find a better.
Um,
Yes, you're talking about this period
yeah.
here. Yeah, the short answer is we're not totally sure. There are a few DO events that happen, I think, on sort of either side of this. Like there are two little peaks here, and both sort of
Mhm.
correspond to DO events. So that's sort of our leading theory, but we haven't looked into the dynamics of why that might be happening, and why the magnitude of the change is so strong. So if you have any theories, I'd be happy to hear them.
Yeah, no, I was just wondering because I mean you see a pretty strong correspondence with sea level. Um, the other question is how sure are we that the sea level curve is correct?
Um, I mean, I'm not a sea level
At
person.
that resolution, right? Because the
Yeah,
resolution of these sea level curves is well, usually relatively coarse.
yeah. So the sea level reconstruction I'm using is, I can't remember the name of it right now, but it's Tamara Pico's from, she's at UC Santa Cruz, I think.
Mhm.
Um, so she would be the person to ask. So I'm not super sure. Are you talking about like the temporal resolution or the resolution of like the gridded data set to pull sea level from?
Um, I was so this is from a gridded data set.
Yes, yeah. Yeah,
Okay.
so the sea level I'm showing here is GOT stands for Gulf of Tonkin, so it's the body of
Okay, so
water
it's
that's right
already a
above
local
it.
one.
Yeah. Yeah, so
Okay.
I think it's pretty like of the sea level reconstructions we have, I think this is pretty specific to the study site.
Mm, okay. All right. And another question, which you probably expect. Do you plan any monitoring in that cave to
Yeah, that
get a little bit better grip on step two of your calculations?
yeah, I mean that's a really good question. So I think the plan maybe probably have to talk to Kathleen Johnson and Mick about this because they're writing grants to try to get more funding. But what would really be great is to get a modern sample from this cave. You know, this
Mhm.
the earliest date we have is, 4,000 years ago. But I think in a perfect world, we'd have a modern sample and then regular drip water and precipitation amount monitoring to be able to directly compare.
Yeah,
So I think
exactly.
that would be like the ideal plan.
And
Um,
then and it seems that you have quite the picture that you showed where you have these beautiful candle stalagmites. If you would go for a drip site that has very similar morphology as the stalagmite that you have, maybe you also captured relatively similar drip site characteristics.
yeah, that's a really good recommendation. We're actually going to the field in a couple of weeks. So I think that is something we should look around for. I hadn't thought about that personally, but yeah, that's a good suggestion.
Okay. Yep. Those were my two questions that popped up. Thanks.
Mhm.
I have one question. In the reconstruction comparison, you have shown that it is not matching really well with the other published records from China and other regions. Have you compared the paleoclimate simulations result from the other part of the world, like Sri Lanka or something? Because timing is kind of similar, like autumn rainfall and the main rainfall period in Sri Lanka or southern part of India. So, do you see any correspondence between those record and any uh, effect of IOD events?
Yeah, that's a really good question. I haven't directly compared them. I think my guess is that the sea level story that I'm seeing in this record is very strong. I wouldn't necessarily I mean, maybe I wouldn't expect to see the same thing in sort of the Sri Lanka region, but I think it would be interesting to compare because they also have an autumn monsoon. If you looked at maybe decadal timescales or something where the big sea level signal isn't so large to see if there were similarities. So I think that's a good idea. But I know no, I haven't compared them yet.
Is there any more question? If not, then let's conclude this session. And thanks again, Elizabeth, for this wonderful presentation.
Yeah, of course. Thanks everyone for coming.